Hi folks and happy Friday. So yesterday we looked at standard deviation for the first time, which was a measurement of how spread out data is from the mean. And as it turns out, there's two different kinds of standard deviation. So that's what we're going to look at today. We're going to look at what those two kinds of standard deviation are and what the difference is. So first up, what are those two different kinds? The one that we looked at yesterday was actually called the population standard deviation, and I know I mentioned it. And in our notes yesterday, we were using the letter S. We should actually be using this letter here, which is the Greek letter sigma. It's a lowercase Greek letter. And so the population standard deviation, just like in its name, is used when the data represents the entire population, whatever it is. So when the data represents the entire population, whatever that may be. So that's what population standard deviation is. We can also have a sample standard deviation. And so that's our second kind of standard deviation. And this one is actually using the letter S there. And a sample standard deviation, just like in the name again, is used when the data only represents a sample of a larger population. So it's used when the data represents a sample of a larger population. So I encourage you to take a look at these two formulas here. On the left-hand side, you've got the population standard deviation, and on the right-hand side, you've got the sample standard deviation. And you might be saying to yourself, well, they're exactly the same. And they are almost exactly the same, except for the thing that's being divided here. In our population standard deviation, we're dividing by n. In our sample standard deviation, we are dividing by n minus 1. So if we break that down, okay, sigma represents the population standard deviation, whereas S represents the sample standard deviation. In both of them, this uppercase sigma represents the sum of, it's an uppercase sigma. It's actually the uppercase letter of this little guy here. So lowercase and uppercase sigma. In this case, it represents the sum of, I should write the sum of, and it's that squares of the differences between the mean, that X bar, and the actual data values. So same calculations as yesterday, we're finding the mean, and then we're finding the distance between the mean and each of those individual values. And so what n was yesterday was it was the number of values. It represented the number of values. So n minus 1 represents 1 less than the number of data values. So the question of why there's a difference here and why it seems to be such a small difference, and that question is actually a really big question. There's a lot of complex analysis that goes into why there has to be a difference here. But the long story short is that if we knew the whole population, the entire population, then our standard deviation would likely be a bit more accurate, and therefore perhaps slightly smaller. We could narrow it, we could refine our calculations and make it would be a slightly smaller standard deviation. But if we're dealing with a sample, then we don't know the whole population. So we want our standard deviation to be slightly larger, slightly bigger, kind of just to cover our bases here. So when I divide by a smaller number, slightly smaller, right? I'm just taking one less. So if I had 1,000 data values, I'm dividing by 999 instead of 1,000. But what that does is it makes our standard deviation slightly bigger than it would be for the whole population. But otherwise, that is the only difference between the two. And so when we calculate standard deviation, it's important to think about which standard deviation we're using, and it depends, of course, on the context. So a couple of examples here. So if you follow along with those examples with me, example 1, a teacher sets an exam for his students. The teacher wants to summarize the results the students attained as a mean, standard deviation, and which standard deviation should be used. Well, if we consider who the population is this teacher's students. And I think for that, we could very well have information from the entire population. So his data, he's not just taking 10 out of 150 students, he's taking data that represents the entire population, which in this case, again, is his students. So this time we would be dividing by n because we would know exactly the full population here. Example 2, on the other hand, it says a researcher has recruited males aged 45 to 65 years old for an exercise training study to investigate risk markers for heart disease like cholesterol. And which standard deviation should be used? Well, so if we're recruiting males aged 45 to 65 years old, there are millions of men in the country right now who meet that criteria, and potentially, a billion in the world. So this has to be a sample. We can't possibly research or ask all of the males who meet that criteria. So we can't possibly include, scroll up just a little bit, all men 45 to 65 years old. So his data, I'm assuming about the researcher there, his data represents a sample of the larger population. Now, so in these cases, the context makes it pretty clear, right? If we are dealing with a population, okay, great, population. If we're dealing with a sample, great, a sample. If we're dealing with no context whatsoever, at least for the purpose of our class, we can make an assumption and use the population standard deviation. Just because we don't have a context, we're just going to assume that that is the entire population. So if we go back a little bit to yesterday's notes, yesterday we looked at this table that talked about the hurricane strikes over the course of decades from 1851 to 2000. And we calculated the mean, right, X bar, to be 17.6 hurricanes. And our standard deviation was a population standard deviation because we had all of the hurricane data. So lowercase sigma was equal to 3.517 approximately. So it's not just calculating standard deviation. You did that quite a bit yesterday, and you're going to do a couple more examples today. But we can also think about data within standard deviations. So the first thing we're going to do is we're going to plot the points from the table on the number line below. So I'm just going to plot in order, and I'm going to mark each number with a dot above. So 19, 15, 20, 22, 21, 18, 21 gets another dot there, 13, oops, where'd you go, 13, 19 gets a second dot as well, 24, 17, 14, 12, 15 gets another dot, and 14 gets another dot. So just a different visualization of this data. We can see it's spread out from 12 to 24. And so we're going to draw a line at the mean and label it. So our mean was 17.6. So I'm going to go just past halfway between 17 and 18. I'm going to call that X bar 17.6. So I can see that that's a center of measure here. I've got 1, 2, 3, 4, 5, 6, 7 values below it and 8 values above it, so not a bad center there. But then it's going to say from the mean, add and subtract 1 standard deviation. So from the mean, I'm going to add 1 standard deviation. I'm going to add 3.517. And if I do that, I'm going to get, oops, maybe a little bit closer there. I'm going to get 21.117. So I'm adding 1 standard deviation to the mean. But if I go in the other direction, then obviously I'm subtracting 1 standard deviation. And 17.6 minus 3.517 is equal to just more than 14. It's 14.083, and that's minus 1 standard deviation. And then we're going to do it again. We're gonna go one step further, and now we're actually going to have a second standard deviation in both directions there. So I can go from my plus 1 standard deviation to get my plus 2 standard deviations, which in this case would be 24.634. And then going back, another standard deviation gets me to 10.566. So if we think about the standard deviation as a measure of the spread from the mean, so again, that mean there is right in the center, we're thinking about how far is everything spread out from that kind of center of the data. So this question, how many data points are within 1 standard deviation of the mean? Well, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 values that fit within that range that represents 1 standard deviation, right? And then within 2 standard deviations, now I'm extending my range to what we just marked. This is going to be our 2 standard deviations, and actually all 15 of our values, which means that what percent do not lie within those. In this case, it happens to be 0%, but that's not always the case. So some questions, or like the next example, that you're going to see are asking us to compare data values to not just the mean and not just to the standard deviation, but to say within how many standard deviations does this fall. And that's important because it tells us, the larger or smaller a standard deviation is, tells us how spread out data is. And if more data lies closer to the mean, perhaps that data is stronger. So we're going to do one more example together just to see how, again, we can use this to describe data. So we have this lovely little data set, 5, 9, 15, 24, 25, 27. So 6 numbers with no context, but that's okay. It has a mean, right? It has an X bar of 17.5. It has a standard deviation of about 8.5. For our purposes, we're just going to say that it's 8.5. So it says, within how many standard deviations of the mean do all the values fall? So we know that our mean is 17.5, right there in the, quote unquote, middle. So if we go 1 standard deviation away or 1 standard deviation away in either direction, that means that we are adding 8.5 or subtracting 8.5. We're adding or subtracting 1 standard deviation. And so I would get the values. 17.5 plus 8.5 is 26. And 17.5 minus 8.5 is 9. Now, if I look at my values between 9 and 26, well, that covers 4 of them, but I've got 5 and 27 that are still outside of that. So I'm going to extend this further. I'm going to go another standard deviation away. So every time I add or subtract 8.5 here, I'm moving one standard deviation away further from the mean. So when I do that, 26 plus 8.5 will get me to 34.5, and 9 minus 8.5 will get me to 0.5. And so now I'm thinking, oh, do all my data values lie between 0.5 and 34.5? Yes. So I've met that criteria, 2 standard deviations away from the mean. So it took me kind of 2 iterations, right? Adding 1 standard deviation to actually adding 2 standard deviations, or subtracting 1 standard deviation to get me there. Now, when it says how many values fall within, 1 standard deviation of the mean, we actually already answered that question earlier, because 1 standard deviation is 9 to 26, and we said earlier that 4 of those values fall within that range. And then the last question, it says, within how many standard deviations would 35 fall? So if 35 was included in my data set, how far away would I have to go? Well, 34.5 was my plus 2 standard deviations, right? It was 2 standard deviations away. So I would actually have to go to the 3rd standard deviation, which in this case, I believe, let's see, that'd be 35, that'd be 43 to actually get 35, right? My 35 would be in between those two. So I would have to go 3 standard deviations away. So I know that right now standard deviation isn't a very firmly rooted concept, but again, we're thinking about it as a measurement of the data, a way to describe our data. So for right now, we're just going to continue kind of calculating it, exploring it, and using it to kind of break down data into smaller groupings. So take some time now to work on your practice assignment, help each other out if you need it, and have a wonderful weekend.